by Dr. Amit Kesarkar, Senior Scientist at NARL Gadanki, ISRO. He'll be talking on data assimilation experiments at NARL. So, Dr. Kesarkar has been in NARL since 2008. Yeah? So he has made seminal contributions to data assimilation experiments. They have an operational model which is running presently at their center, which is disseminating very useful information for ISRO's launches at SHAR. I request Dr. Kesarkar to give his talk. Thank you.
Hello, good afternoon, and nice to see you all here. I am happy to see a lot of young faces because each time you ask Amit, only we people are meeting and then no young generation. So I'm very happy to see all of you. So over the years, we have done a lot of things in data assimilation, and yesterday Jyoti has also talked about different aspect of data assimilation, what we are doing at NARL and hands-on on that. What I am going to do is, I will talk on how data assimilation is useful to something else, to derive some important information, to write down a new theory and all. So what kind of experiment you can do so that you can solve unsolved problems in the atmospheric, climate, and even hydrology or many domains. So I am Amit, and this is my wonderful team who has really worked hard to achieve a lot of things in the DA, and I will be presenting some of their work. Some of them are my research student, PhD students, and some of them are scientists from our organization, and they contributed a lot for this activity. So just wanted to know, after this workshop, who do not know DA? All of you know DA? Yes. So we do data assimilation, generally for operational or research purpose. Research objective is to improve the knowledge, and operational objective is to better prediction. Now, in research, there are two components. One is forecast, sorry, here spelling mistake, and another is reanalysis. So reanalysis is generally done to understand the physical phenomena. Once you understand the physical phenomena and then parameterize it, then again it will lead to the model improvement or DA improvement. We do the error analysis, and if it is improved, then we go for operation and better prediction. So over the year, this cycle keeps on developing. So it is not that if you are doing research, you are not contributing to operation, or if you are doing only operation, you are not contributing to research, because both are linked. You cannot separate them each other. Rather, without research, you cannot do operation. So research in DA is very much useful. If your prediction is not improved, then look into model or DA improvement and all, and again you do same loop. So what I am going to talk on is NARL high resolution weather prediction system. I will be brief about that. Then what research we did for operational improvement, and some of the concept of new model development at NARL. This is required, and all I will come why it is required, and so on and so forth. So we have a one project which is called as popularly known as Chittur project, and this project is to develop a high resolution weather prediction system at mandal level to predict the prediction over heterogeneous terrain of Chittur. Now, why this mandal level or that? Because farmers are very much useful. They want this forecast. Rather, 2 days back I was discussing with one of the university professors. So he was telling that with the initial condition of June, you predict what will happen in March, how much temperature of the next year, how much temperature range will be there. From there, they will calculate the yield of the mango crop. So you think that this mango crop undergoes different phenomenological changes, and they want forecast as different stages. But as you are working in the atmospheric science, You are aware that it is very difficult to start at March, start at June and give prediction in March, so that what will be the range of temperature, temperature range is maximum to minimum in June. This is in March. This is required for them because the temperature range will control the flowering of mangoes. And you know that this year there was a heat wave, and heat wave actually reduced the temperature range. So temperatures were from 32 to 38 or 32 to 45. So that range, night time, if it is not cooling, what happened, there is some fluorescent hormones in the plants, they are not getting developed, and obviously you have impact on flowering. And this year, because of the heat wave, we have 10 to 15% of mango in Chittoor region or those regions, or what we can say South Andhra Pradesh. Same is case of Maharashtra, same is. So expectations are lot. We have mathematics, we have model, we have techniques. Model, I mean AI, ML and all you can take. But however, that predictability is not there. So there is a famous paper by Lawrence which says that we cannot go beyond certain steps of predictability. And recently, 2 papers, I will be discussing them, published by Bow and Chen, which also talks of something. We cannot go beyond prediction, and people are trying hard to improve the model, improve the DA technique in different perspective to go there. So aim is to continuously improve the weather prediction. So we did this to work, and we are working on this. And if you want more information, kindly contact me, Jyoti or Pawnee. They will able to give you more information on that. So this is our domain. So outer domain is we are covering all Eurasia, then South Asia for 4 kilometers, South India for 1.3 kilometer, and then the South Andhra Pradesh for 440 meter. Now you will ask me why this much big domain is required. Second thing is why this 400 meter resolution you require. Now when you talk of under level, or if you go to farmer and talk with them, they will say that whether it will rain in my field or not. You answer that. I am not worried about others. Another thing is if you want to account what all systems which travels to this region in now prediction time. So we are going for 7 days prediction, and you envelop that region, it's really goes up to that. So some disturbance which is happening here will travel to this region in 7 days. So if you don't account that, what will happen is always through boundary instability start coming, and your prediction will not be accurate. So if you go beyond 7 days, you need to go for the global model and global data assimilation, global and all. But then you cannot go to very high resolution. And for that purpose, these domains were selected, and complexity is very high. We have around 1.67 petaflop computing system, and we are using this for generating this, that. You can see the product at forecast.narl.go.in. Actually, Jyoti and Pawnee is backbone of that. You can see, I do not know whether I can go and show you. Otherwise, let it be. You can really visit this. You can get, even you can visit from this thing. Once we have this, we have data assimilation, and we have developed this algorithm based on lot of understanding, which I will talk later. So here what this algorithm does is it goes 12 hours previous, then generate the 12-hour forecast and use those forecast output for assimilation. It has 70 members ensemble. So you have plus or minus 3 hours. So 7 input files. Each is split up with 10 member ensemble. So total it becomes 70 member ensemble. And then those 70 member ensemble goes in 4D and VAT, and then improved initial and boundary condition and generate post this forecast. So it's used 4D NVAR with 64 levels and 0.44 kilometer. It does lot of data assimilation, which yesterday Jyoti might have told you. And then we validate over our region. So this is like IMERGE data, which is 0.1 degree, and this is what thunderstorms over Gadanki, and you can see these flows are well simulated. Similarly, with IMD, if you go for 12 kilometers, you will see this 4 kilometer like this. But if you really go to 1.33 or 0.44 kilometer, you can isolate a thunderstorm, you can see. So this is how we can separate the amount of rainfall spatially. Now, then you will ask me the question, how much maximum resolution you need, highest resolution you need to answer the farmers, like when we are talking to mandal level. So nowadays, one person may be having 1 or 2 acre land. Nobody is having hundreds of acres. If we go for 0.44 kilometer, this amounts to 0.44 by 0.44 kilometer, it's amount to 68 acres land. So you are not helping farmer. Really you need 63 meter resolution. So we need to go to that. And then that is the work you people need to do in future to help the farmer. Then get that into real time. Real time data will be available with him. He can use IoT for controlling some of his irrigation kind of practices and so on and so forth. So lot of work for young generation, and therefore I am happy to see lot of young people here. Still we did, and we could get 75-degree accuracy. This is because of cyclic data assimilation we are doing. So first we are improving the initial conditions. This one? Yeah, this is really big. But if you see this domain in 12 kilometer, you will see this all region will have rainfall. Then you will say this many months. Where is this full domain? This full domain. Yeah, we are plotting that to show, if you see in 12 kilometer, how things will look like. And if you want to satisfy a local farmer, you need to go like this. These dots are actually where the rainfall occur. So you see that 2-3 kilometer rainfall and then no rainfall. But if you go for a coarser resolution, it will average out all over that full area. Means total, it will total out full area, and you will not able to say. So what you will say that these 10 villages will get the rainfall. Out of 10, 2 villages will get, remaining the people are saying. Then there was a joke, actually expectation high. I cannot tell this in this forum, but this happened in ISRO also. We were expecting rainfall in some place, but it occurred 2 kilometers away. They laughed at us. So these are the expectations from the users. So we cannot do. So we have to help them to get the information. But this 75% accuracy is really came after a lot of efforts, and we are successful. Then we had we could get the data from Avanantapur and Satyasai district under this collaboration with NG Ranga University, and we could calculate, and you will see that those who studied the meteorology, the bias is 2.3 mm. You mean stress. So we could go to that accuracy, but only over small domain. It is not that, and then we validated various cyclones over our region. This is Pauni's paper in JESS, and you can see they are doing well. So a lot of things we are doing in operationally to improve weather forecast. We validate them and all. So these are a few papers. There are many other papers which I have not mentioned here, like Jyoti's paper on UNFUN and all, to improve the weather prediction and all. But these are required. This output is coming after lot of them. Initially we were started with 27, 9, 3 kilometer, then with 3D, simple 3D data assimilation technique, or before that we started with only nudging, and over the years we could really come to this stage. So this is because we involved in very good research, and therefore I will be talking on research for improvement of operational weather prediction and how data assimilation is useful. This is one of my favorite topic, and how many of you know marsupial paradigm of tropical cyclone? Obviously Arpita knows, Pawnee knows, maybe Jyoti knows. So what is marsupial paradigm? Like a child takes birth in womb of mother. Like kangaroo, small child, which actually sits with mother, then only it will grow. So you might have seen many such a small clouds when you are flying. When if you go out, you can see them. They form thunderstorms, and such a thunderstorms really comes together to form a tropical cyclone. So how these small incipient disturbances, they come together, organize, merge, collide to form a very big cyclone is a question which is unsolved. This is Montgomery's paper. So Gray in 1998, what he wrote, this clustering is happening under some kind of wave activity. So that wave is a mother wave which protects those incipient disturbances to come together. They are shielded from the environmental shear so that they come together to increase very high vorticity, and this is how they cluster, and there is an exchange from meso. Now you may not be knowing, or some of you may be knowing, how many of you know meso gamma, meso alpha scale? So there is an exchange of 1 to 2 kilometer spatial radius. The energy is generated due to the condensation or latent heat release to higher scale of 20 to 200 kilometer, and from synoptic scale to 20 to 200 kilometer, and that thing comes together, and which is protected by what we call as Cauchy-Lagrangian cyclonic circulation. This gives us enormous energy inside that particular closed circulation and forms a cyclone. This is called as marsupial paradigm. So this was proposed in 2006, and you might have heard like Sisk or Wish theory of Emmanuel and all those papers. So this. So idea was there was a one cyclone Agni, which actually formed very near 0.6 degree from the equator. All of you know no cyclone forms near to equator because Coriolis force is less. Then what happened? It go on south of the equator and again come back to north, and it hit Oman and all. The question is how that cyclone developed. Now you have ocean observation very sparsely, a whole over the ocean, both ocean, you have hundreds of observations. Not at the resolution of this scale is happening. So you have to go to 2 kilometers. You don't have observation. Satellite data, that is also not there. Nowadays 4 kilometer satellite data is available. Those days was not there. Then the only way that you generate reanalysis, which is high resolution reanalysis, verify wherever the observations are available with you and say that my analysis is okay here, so I propose. Okay? So this is where you people need to do, why things are not happening, why things are happening. You need to get into the answers of that, and this we did in 2006, and you can see there that how this merging of different small vortices or here forms a big cyclone. So it was not possible if you don't use the data assimilation. And here what data assimilation technique we are using is cyclic continuous data assimilation. You might have heard in the previous lectures. So we did each 6-hourly data assimilation, predicted for 6 hours. That 6 hours we added more observation and continuously we did. So data assimilation is so powerful when you want to give the explanation of particular phenomena, maybe ionospheric phenomena, meteorological phenomena, atmospheric phenomena, hydrological phenomena. If you create some background and add data into that and see that you do a lot of experiment and finally you will find out somewhere, at least at particular positions, you have reasonably accurate simulation. Those simulation you take, then analyze what was the physical cost to why it is happening, and then then you can do that. And this was success. I presented this in NCAR that time, and it was like WRF was just coming. 2004 WRF came, and 2006 we presented, and it was boom. Over those years, we have analyzed many cyclones. We validated them and tried to find out how these vortices finally give rise to different kind of cyclones. And many of these are available in different papers of my PhD students. And if you want this, I can give you, or I have written here the references. They are available free of cost to download. And we've told that vertical hot towers are main reason for genesis of tropical cyclone. So what caused cyclone formation was one of the answer we could get. If we would not have data simulation technique, we would have not able to do that. So it is, so what you required, like you, Professor Varan might have taught you, like you required one M and you required data. That M is your model. So we were having WRF that time, and you need data, you assimilate them, validate it with independent observation, and where you are matching, there you say that now, because you are having then 2 by 2 kilometer reanalysis. And based on that understanding, you can specify that. This is how. There was interesting discussion happened, because when we talked of vertical hot tower, this is one of the famous cyclone Madhi, which was having very peculiar track. Oh, I have not included here, but so yeah, here. So one of the, in discussion, some of them people ask, then your Bay of Bengal is very much moist. Our Atlantic is very much dusty. Okay, then how it will affect? Can you talk on that? And this is how we got another paper. So there is a 2 cyclone. One is Madhi over Indian Ocean or Bay of Bengal, and another is Florence over Atlantic. And what we found that the Saharan dust, which is intruding inside those cyclone, which actually give rise to a delay in intensification, which cause cyclone to be more broader or in area and then more violent. And we could and these results are available. So here also we did WRF 3D WAR analysis, and we compared and all. So what you are learning is not only the theory of data assimilation, but it is one of the tool which you need to use it for discovering something new theory, new whatever you may be working, you can do that. Similar thing we did for rapid intensification, eyeball replacement. Then once we have tool, you keep on playing whether it explain this, it not explain this, and so on and so forth. And we could also answer why this Oki, instead of hitting Gujarat coast, it died out over the ocean. So many such analysis we do that. Once we did that, question was asked, why you need 2 kilometer reanalysis? Why you need HPC? You can have, there are plenty of data sets available, right? ERA, MERA, ERA Interim, JERA, whatever. You might have heard this name, right? You may be using also. Then, to answer that question, we again got into another discussion that which global reanalysis provide tropical cyclone structure and intensity over North Indian Ocean, and we need to downscale those. And this is available again in another our paper contribution, and we have analyzed many data set and we compared with IMD best track data set, thinking that IMD is giving better position than JTWC and other aspect, and we could come out with different. For example, if you see, this is contingency table, this is the observed and this is the predicted. So if observed is predict, we have analyzed many cyclones, and therefore if observed are depression and prediction is also depression, or ERA data is representing depression, those many points you will get it here. So if you see many of these analysis, for example ERA interim or JERA, they are not represent higher intensification. For example, observed was cyclonic storm, but it was not representing. So you need to analyze available reanalysis before using them, because otherwise you can download easily, use them, but then they will give you misunderstanding or the misinformation. And for that purpose, we did this analysis, and we could find GFS analysis and ERA5 able to represent the intensification of cyclone up to very severe cyclonic storm, not more than that, but they are better. Then we analyze different structure, and you can see that ERA5 is having better and GF is having better structure, others are not. So what we did is physical understanding based on that we come up with the final summary that ERA5 and GFS are better for this. Why this is required? Then you select your initial condition, like you need base as GFS or ERA5. If you are solving tropical cyclone problem, if you are solving some westerly waves or so, how STWJ is moving, then you go for another. But at least first you verify that. Then another question we ask, which data assimilation we should have? Because now we have everything. We can run 3D var, 4D var, 4D NVAR, 3D NVAR. And we did all those experiments, and then we find, taking GFS as a base, which particular simulation captures rapidly intensification, and this is another contribution available with our group, and we did this, and it is available online. I have given the references so that some of you doing PhD, they can go through and you can write a paper based on similar thinking. And we did so many cyclones, and these are the domains. And what we did is continuous cyclic assimilation, where we are taking the plus minus 3 hours as a this one, and going for 12-hour forecast, ignoring plus first 6 hours for spin up, and take this forecast, then in this initial condition assimilate, then take this forecast, then again, and use this hourly outputs for analysis. So this is how you can keep on cycling and get a better this one. And then we were happy, like IMD, DWI showing proper, our cyclone is also simulated better way, and we did for each stage what is the error in track, and then error in Vmax and MSLP, and finally we found that 4D NVAR is better simulating this one than 4D VAR and any other, but it takes a lot of time. You need the HPC. 3D NVAR is marginally less. So if you don't have HPC that much, you can even go with 3D NVAR, but if you have privilege to having HPC, you can go for 4D NVAR. No, we generate cyclic reanalysis for same time. So what we did is 0 GMT to 6 GMT, we go up to 12 GMT. So 6 GMT forecast you got. You ignore this for spin up. Take this here. So here. So 0 to 6. Now for next, this is the initial condition. as a time window. Same. No, plus minus 1 hour.
0 to 1.
Shall initial. No.
You will use 0 as a initial.
Initial condition 0, but my window is -1 to +1. See, even for everything, 0 is a initial condition. Then you go for the 6-hour prediction. From that 6 hour plus minus we are using. We go for other, but bootstrapping has one hour back. So it's bootstrapped. So these are the various data set assimilated, and this is all. So similarly ensemble, because you know that bootstrapping option you need to on and also see. So this is the way. Now what will happen? 6-hour to 12-hour forecast doesn't deviate much. Then these 6 hours to 12 hours you join them together, then you have a large amount of reanalysis which is very near to the observation. This is how, so you know that what we need to 6 hours and implicit too. So then we did this and we say that 4D and where. Now that is the reason why in real time now we are going cyclic 12 hours previous. We wanted to do each 6 hours, but we could not do because of HPC limitation. But our current HPC provide us 12-hour previous initial condition forecast for 12 hours, assimilate here, and then use 4D and where. Our smaller HPC, we were using 4D where or 3D and where, this one. So unless you do research in this, you will not. Now if you see, this is not data assimilation research, it is something related to atmospheric science. That is true, but unless you get those features in the model, you will not able to get into the, in reanalysis, you will not be able to get in the forecast. If you see, reanalysis generated from this flow are pretty accurate. Your errors are too low. But if you go for forecast, your errors after 12 hours are diverging, and that is the question we need to solve. Then we had a privilege to have SketchSat1 project with SAC Ahmedabad. Prashant was our reviewer for this project, and then whether we can go, how this SketchSat1 data assimilation help to improve the cyclone forecast, because you know that surface data or the surface winds matters. Any surface boundary condition matters, and whether it improves or not, that was the question. And we did that, and many publications came out of that. And then like AOSG from SAC, and then IIST Trivandrum we had. Again, where the Arpita was working, and we did this. We assimilated OSCAT, SCAT, WinSat data, and obviously GDAN series. There are many papers came out of this, but I will be presenting very few results which are very much important. For example, SCATSAT has limitation more than 25 meter per second because of the sensor limitation. It cannot simulate, but you can see here reanalysis generated is going more than 30 meter per second. Okay, so that is where you say that in your blue Brace linear estimates that your error is much lower than the sensors and model, and this is where this improvement we could see. Similarly, at maximum intensified stage, we could get better wind speed simulated than ERA 5 and all. So similarly, rapid intensification is better simulated in the generated reanalysis, and rainfall is validated with GPM is getting good thing. You know that why rainfall is important for tropical cyclone simulation and so on. So then we got more confidence that what we are doing is proper, and we gone further. But there was a mandate for us to do something related to diurnal cycle of rainfall and precipitation, where Jyoti was working, and to improve the representation of Diana cycle in the model, and we did a lot of things for development of thunderstorms over our region, especially what we are seeing high resolution region, and we could show that how this gravity flow is generating thunderstorm over Gadanki, and we have analyzed the different reasons, like this is bulk Richardson number and shears and vorticity, how it is generated, and we found that the directional wind shear is playing more important role. But most important is reanalysis generating on that time at that intensity of thunderstorm in reanalysis. But if you go for forecast, you are off by 6 hours, 3 hours, 4 hours and all. So question is there, and based on hundreds of thunderstorms we simulated, we could come up with what is the preconditioning and triggering mechanism. Why suddenly thunderstorm occurs at that time, that position, we could answer. And for Gadanki, Chennai, Sriharikota region, we know why thunderstorm happening and all. Then again Jyoti stepped in. In this situation, sorry, this is a movie not playing here. We have X-band radar, and we did rapid update cycle each hourly for X-band data assimilation. So we recalculated lat-lon and converted those lat-lon into a model for ready format, and then this one. So during such a thunderstorm event, we can have this. The advantage is, okay, I will talk because the data. So this is the radial velocity operator, and this is the Doppler radar reflectivity operator. We assimilated using these two operators, and we could find that the improvement, this is control run and this is radar and DA run. So we found that the vertical velocity represented, therefore your REN is properly represented, clouds are properly represented, and so on and so forth. So this is how you get the improvement in your conditions. So finally, if you see the control run and I-merge run, at least some REN we will able to simulate, and which will able to tell us that thunderstorm will be there, rainfall will be there, and so on. But where we failed, because always you are not getting success. This is a particular thunderstorm which was occurred on 31st August night time. Whole night I was wake up, so that it should not affect this region, and the flow was from this region, and these are the Sri Kalahasti hills. Some of you might have gone there, and thunderstorm was coming here, and we need to ensure that thunderstorm should not affect this region. And for that purpose, we were continuously monitoring Doppler radar. But what happened, you know, here this Kalahasti god, Shri Shiva Shankara, has saved this region, because the thunderstorm divert in both directions and nothing happened here. This is a typical case where the land surface data assimilation or the land surface representation plays a very much important role, and therefore you need to go for the very high resolution, the best you can do. I cannot talk everything, you may be understanding what I am saying, but so unless we go sub-kilometer resolution, resolve the topography, resolve, all of you know that fraud number, this fraud number was not more, so that thunderstorm diverts in the two channels. Otherwise, if it would have overcome these hills, it would have affected this region. So that was a practical problem we were facing. We were literally sweating, and these are there. Then what happened, suddenly we were doing a lot of these things, because our main region is Chennai, Sriharikota and Gadanki region. But suddenly one student came from Jammu Kashmir, and he wanted to know how Jammu Kashmir is getting heavy rainfall, because he was talking, you are doing a lot of things in cyclone, this is something western disturbance. Then I told him that western disturbance, if you go from the surface to 700 HP is a circulation, and above that it is a trough. So it is a hybrid between extratropical cyclone and tropical cyclone because it is in between. And then we started this analysis. We come up with, now you may be knowing Artel potential vorticity, you need to see that how it is tracking, and then where is the conversion and how baroclinic instability plays an important role, and how this kinetic energy plays a role. And we could find out the decreasing in meridional component of kinetic energy and increasing zonal component of energy caused the stagnation of cloud mass over western Himalaya, which gave the high rainfall and all. So we did for many, more than 30 western disturbances, and we could come out with different things. Interesting thing happened. We were doing everything in the meteorology, but there was a Government of India project, National Carbonaceous Aerosol Program, and which wanted to know how impact of assimilation of meteorology will improve the simulation of atmospheric chemistry. This is the paper. But here one limitation, when we were doing for meteorology, 6 hourly cyclic we were doing. But here, for a simulation of solar cycle, 12 hours, you have to live like that, because they want to see that how aerosols are responding to changes in the solar brightness, solar diurnal cycle, means solar insulation at surface, and so on. So instead of developing 6 hourly reanalysis, we use same technique but 12 hourly, and using that 12 hourly reanalysis, this is here we use 3D wire, simple 3D wire DA, and we use era entry. We could see that the dimming effect and changes in the surface temperature by 2 degree can be simulated, and this impact. So this is something called, this is something like how 3D wire DA in meteorology affects the WRF-chem simulation in that. So you can get the dimming effect and changes in the surface temperature, we could get it. This is published in that. So a lot of things I told, which is research. Lot of things happened, but U-turn came when we wrote this paper with Bovenchen. I was mentioning to Amit yesterday, dual nature of chaos in the atmosphere. So all of you know weather is chaotic. Many of you know butterfly effect from Lorentz. Many of you know convective cloud development inside subgrid. But actually what happening is, we think weather is monostable. Means if turbulence is there, like skiing, you have the turbulence. But weather is, so therefore the dependence on initial condition, singular dependence on initial condition is important. But weather is not only a chaotic. There is a no chaotic component also inside the subgrid, but we assume that as a chaotic, and because of that there is an error in the prediction. So if you see this kiting where the stable part of the flow is there, and as well as you have the turbulence flow. So you have in subgrid the dependence on initial conditions, that is where the data assimilation is very much useful, and there is a no dependence on initial condition, which we are not simulating. So we need some technique, advanced data assimilation technique, which resolve this is a stable condition in subgrid, and this is a dependence, initial condition dependence. Then do you improve this? Don't improve this. And this is where chaos. By the time we publish this paper, Bovenchen come up with another paper. There are 3 kind of butterfly effect, not 2 kind of. So this is something interesting. Like something we are saying that monostable and multistable, but there is something more than that. And these 3 kind of butterfly effect are, one is sensitivity dependence of solution to initial conditions, and therefore we do these data assimilation, improve the initial condition and then give the forecast. But another is a tiny perturbation can create a organized circulation at larger distance. So after data assimilation, you need to ensure this should not be happen. Either you put some kind of filtering process, which is Weiss filter and all, or there is a another kind of thing is hypothetical role of small scale processes contributing finite predictive. This is what I was mentioning when we are talking of tropical cyclone, that something which is less than 2 kilometers is contributing to here, yes. Something which is less than 2 kilometers latent heating contributing to 20 to 200 kilometers. And if it is not properly represented in the model, what will happen? So it is not a single butterfly effect, like a single initial condition, error in the initial condition can create a very large cyclone in some other region, but it is something like this process is not properly represented, also create similar thing. So it is a combination of three kind of butterfly effect, and therefore whatever we have done, we got success. But more than that, what is very much important is we need to account for these all three kind of data assimilation, three kind of butterfly effect. We have to segregate them. We have to write down the algorithm to improve their this one. And once we improve, so a lot of mathematics is required, and that is the challenge for young generation. In future, you will find out this thing. And that is why then we decided to develop another model, which we call that as a unified polyhedral framework for weather and climate modeling. So I was mentioning where Jyoti's research that diurnal variation improvement is, if you improve the diurnal variation properly inside the model, it will definitely improve your weather as well as climate, because average will be also better instead of representing what cumulus parameterizations nowadays indicating. I'm sorry, I'm going up and down. So I'm going wrong way. Yeah, here. So cumulus parameterization represent cloud like this, but if you do it properly, represent it and all, and that was the one of the reason why we went that. So what is our model is? Again, this is a movie. I do not know, I can play there. This resolution is adaptive to particular thing. So either to topography, either to coastline, either to development of thunderstorm, development of convection. So this goes from few kilometer resolution to meter scale, and it resolves the processes. So if you think you have 1 kilometer resolution model, inside you divided that into 1000 by 1000 grids, and there each, now we have triangular grid, polyhedral grid, but you think each square is resolved whether it is stable or it is not stable. And accordingly you give the approximation and then you predict, which will be much more better compared to this thing. And there are many such publications, and followed by we are developing this microphysics scheme where we are taking care of entrainment. We divided this in microphysics in 8 hydrometeors and aerosols, then lateral and body entrainment, role of infrared killing, intra-cloud turbulence, and so on. We are doing that, and many of these papers are there. If you want this, please let me know, I will send you. So what we did is, there something called as multi-scale and multi-physics. Now how many of you heard of Boltzmann equation? You have done? Navier-Stokes? Navier-Stokes with slip condition? Budger equation? So these are different equations which represents the flow at different this one. And there is something called as Knudsen number. which determine that which particular physics you need to use to represent which flow. So our microphysics scheme takes care of multi-scale. So where the interaction is with say fine particle of aerosol, it goes to that scale. This is something called as multi-scale, means resolution automatically adapted to that scale. Second thing is it does the multi-physics. This is during cloudburst event of Uttarakhand. We have simulated. We have segregated whole. You know that collision collation process. So collector droplet in different beams and small droplets, which is actually colliding with other in another beam, and you see that this particular blue color is indicating that you should use sea flow regime, rarefied gas dynamics for collector and small droplet before the event, but after the event it become rarefied. But however, most of our, rather all of our models in the atmospheric physics use continuum dynamics. So if your approximation fails there itself, then you are representing whole thing with wrong equation. What you will get? Definitely you will get error in the forecast. Then for what you will account? You will account for data or you will account for model physics. But you yourself have not added those physics, then it's a problem. This is in atmospheric research in review, and then we could answer the thing that you need to go for the multiphysics. Then how you will do? Your model will have, if Knudsen number is between this equation you solve. Another if, another if, another if, and then accordingly it will be solved. Then only you will really able to do that. Otherwise what you can do? Use Boltzmann equation for whole range, millimeter scale simulation, molecular dynamic simulation for the cloud, which is not at all possible with current days HPC, and therefore multiphysics and multiscale knew this one. Now you think of, you are writing adjoint or you are writing probably adjoint and all you may be knowing. You might have heard previous lectures about 4D var and 3D var, etc. So for different equations, and then you are inverting your covariance matrix and so on and all, how complex data assimilation technique we need to develop. So this will be demand for future because everybody is begging for the high resolution analysis. Everybody wants that. So previous generation people, they used to say, what new you will do in the equation, but you need to really change the equation. You need to really come up with the new equation or some equations which actually automatically adapt to different thing. Like if you see WRF, it is hydrostatic also non-hydrostatic. It is real-time non-hydrostatic. So similarly, you need to modify the equation, and in those equations, you have to write down the algorithm of the data assimilation. This is your work. This is next 20 years required to come up with these models, but this will give you very much big learning. So then this is our microphysics scheme. Simulates and all, once you do proper equation, and this is collation droplet efficiency. This is in JSTP in review, this one. Besides that, you are working on another scale which is aerosol particle, which has fumigation effect, which has coating, which undergoes coating and so on and so forth. For that purpose, what we have done is we have developed a hybrid Monte Carlo gear solution technique to condense this collision collation model is ready. Yeah, exactly. That is where I was just skip that because it's boring to see because we are talking of data assimilation. So you can see different things and all. These are the collision efficiencies, collision efficiencies and all.
But these are local.
At this moment, local. So finally, what we want to do is this particular thing will automatically adapt to the scale. that scale that microphysics will play in. Then we want to use AI or some kind of statistical approximation to reduce the computational workload, So that is future. That is where one of our meeting I told you we are using MD dynamics and all those things. And this really required lot of, we have not thought of data assimilation at this moment, but future such a data is available. No, this is idealized experiments inside the box and all. So finally your precipitation should come match to actual precipitation. That is the only thing. Because we don't have measurement in the cloud. That is where data assimilation, that is where reanalysis is useful. You cannot measure, go in the cloud, you will perturb the cloud. But once you have some measurement where your reanalysis is accurate for those measurements, then you hypothesize my things are correct. And for example, rainfall, it is coming in very high accurate spatially. This we are doing in 1 meter resolution. So then for a 10 kilometer grid, and if you have multiple AWSs and they are getting simulated properly, then you say that what cloud I have simulated is correct. Unless otherwise I need to find out why it is differed. This is the only way. That is the another perspective I wanted to give, that data assimilation is not like only you change the technique, you find out the error, or you add the data. It is much beyond that. You need to come up with your thinking, your theory, your problems, your this thing. Then come up with your own reanalysis. With that reanalysis, you interpret whether you are getting all physical processes represented correctly or not. If not, again improve this. Then once you get this, then you say that this is because of this. That is where you will do the discovery, and that discovery will have much more importance, and that is only because of data assimilation background. Because you don't have, your satellite cannot resolve the cloud, 1 kilometer inside what is happening, 1 meter even satellite cannot do. You cannot have own equipment going at each this one. Laser will disturb the cloud, you can have a scanning. Validate is what rainfall level, ground, yeah, actual measurement what you have. Or you see the movement of thunderstorm or movement of thing is simulated properly. Like cyclone we did, we validated track. We validated mean sea level pressure. Because we cannot go inside the, there are something called as aerosonde or those drop sonde, aerosonde. Aerosonde goes horizontally, drop sonde goes vertically down, and they measure. And then you can parameterize. That is something different. But this is theoretical idealized experiment with molecular dynamics, DCMC, and all what is Amit's language, like direct simulation, Monte Carlo, and all those things we did. So for this purpose only, to
with your adaptive grids,
yeah,
assimilation becomes
exactly difficult because your matrix changed the size, and that is where I proposed in HIPC.
One or two papers out there discussing this.
Yeah, so in HIPC 2017, I proposed dynamical load balancing. So you have multiple GPUs, we have many cores, 7,000, 10,000 cores, and you have CPU. Suddenly you saw thunderstorm, grid adapted, workload increase, transfer to GPUs, do computation and come back.
So this is for computation. Assimilation also.
So matrix you solve on GPUs.
Technical problem because we don't know what to. Basically, the observation, there is no one single observation of data.
Yeah.
Now there are multiple observation of data.
Yeah, multiple observations. So it's theoretically a big,
Theoretically it's a
big challenge.
I think just one, maybe two papers.
Yeah. So if somebody come out with new thinking, like it's a challenge because all of you are young and you need challenge so that you will come up with something beautiful in future. And that is where, therefore, like Arpita may be knowing that my PhD student, I always say, no easy go. You have to do and show, publish, and then go ahead. But that will yield you something. Then you will say that this is my method, this is my model, this is something. Otherwise, just doing error analysis of output, okay, you will get the paper, but you will be one among the 1,000. But if you do this, you will have your identity, and that is where I want all of you young people to venture into. These papers are not old. You can see this paper is 22 and this paper is 20, both are 22 in your generation. Okay, both these three kind of butterfly effect and all, now people are talking. Today I forwarded that to you also. So this is where theoretical scientists, atmospheric scientists, and many people should come together, join together, do data assimilation, somebody will do parameterization, somebody will do, like Amit was saying, improvement in mathematics of data assimilation and so on and so forth. And then come up with a very good model that will give better focus. For whom? For the people like farmers, for different kind of requirement of society and so on and so on. Then we will have a better prediction. So these all efforts are to improve the predictability. So this is where I was emphasizing, and therefore for CCN estimation inside the microphysics, we have lateral as well as from top and bottom intuition, and for that purpose we went for the Monte Carlo gear solution. We would have only gone for gear solution. Why Monte Carlo? Because there is a lot of uncertainty. Then that uncertainty gets simulated, we did it, then we improve for diurnal variation and then improve for the disastrous events or the extreme event during cyclone, western disturbance and all. These all three papers are published in Science of Total Environment. If you want, I can give you, or they are available online. And similarly, very small perturbation of infrared heating on the lateral part of the cloud. Inside the cloud doesn't affect by lateral heat, but boundaries gets affected. And we could simulate this and come up with a better model for that. These all will combine the better microphysics. And this is how we are improving. Luckily, ISRO has lightning network from NRSC. We are collaborating with them to improve even parameterizing lightning flash count for short range and long range prediction. This will be useful to avoid the death due to lightning and give the early warning and all. So I will not, I think I have not added those slides, yes. So I will not go what we are going to do, but just I will inform you why I am not adding, because it would have been much more bigger this lecture and you would have got bored. I think my time is over, right, almost? Or time is still there? Over. So we are trying to model the net charge density. Now you have collision, collation, rhyming, all processes inside the cloud represented in the microphysics. Then their charge separation. So we call that as a breakdown process. And one of our recently we submitted that paper to modeling of earth science and environment. And that background, charge background, collision background, or you can have ionic background and so on. From that we are trying to get the net charge density. Then using land use land cover, we are estimating what is the ground net charge, whether positive, negative, and there are four ways of charge separations. Like one is below, negative, mid, positive, above, negative, and further above positive, and whether discharge will occur or not, and how many such a discharge will occur, and then prediction will be flash rates. So this is where we are improving this one. We are certain that we may not get in one go, but we have observations of NRSC, and we will come up with this parameterization because there is a lot of physics involved in that, and charge separation, charge generation mechanism using different microphysics model, and with that and changing the land use land cover, how it will happen, then we can answer a question. If you change this forest to CT, what will be the impact of that in lightning forecast? or lightning, this one. So this kind of simulation experiment you can do, and we are working towards that. Any collaboration, anything you want to get involved in, you can get involved in, because this is something new topic. But once this parameter is developed, we can advise the people that don't build city here. You plant trees there, and all those answers you will get. Then you will be satisfied like my research is very much useful to common public. And this is where you need to come up with the new parameterization. So this is how I have not gone through each and every slides, but what I want to emphasize is rapid improvement in DA techniques are seen, and their operationalization seen in last 2 decades, lot of papers, lot of new thinking and lot. But we need to still have to handle 3 kind of butterfly effects, because to only you were handling initial condition dependence through DA, not other 2 kind of butterfly effect. You need to think of new mathematics. Then we need to generate the future generation models which will have complex D algorithm. Then we need to think of how to simplify them, operationalize them, and so on. And there are new avenues for young researchers like you, something called as convective scale data assimilation. Assimilation in multi-resolution, you have multiple resolution, adaptive grid. Multi-scale, I mentioned, like different scales of atoms, molecules are interacting, somewhere parcels are interacting. Then multi-physics, different equations of motion comes into the picture. And multi-stability, you have chaotic, non-chaotic in subgrid process to improve the predictability. I hope this generation will take up this as a challenge and go ahead with that. This is what I wanted to talk about. If you have question, I like to answer. Any question, you can ask simple question also. Okay, but just I wanted to emphasize a lot of work for you. And that is why this particular thing, I am really thankful to Professor Chandrasekar and Dr. Kutty to involve me as an organizer for this particular workshop. And really, I hope you might have learned the basics of data assimilation, and in future you will develop them further and come up with new data assimilation technique. So like 3D where, 4D where, and 4D and where we are listening for years together, we have to listen something new. Like one of them is particle filters or much more advanced mathematics, which will lead to better prediction. If no question, thank you very much for your patience.
Yeah, let us thank Dr. Amit Kesarkar for an excellent lecture. Yeah.
Thank you. Thank you very much.